All right, hello everybody. We're getting into section 6.7 today, talking about bond enthalpy. So you're going to want to grab a calculator, and if you don't have one already, you can take a periodic table and equation sheet. We're going to be doing some math today, so you're going to need something to be able to do that with for our bond enthalpy section here. So bond enthalpy, what is bond enthalpy? Well, enthalpy we've been talking about all unit is that energy, right? And we're talking about the energy of bonds. So in a chemical reaction, we have to break the bonds of our reactants so that they can combine to reform whatever our products are. Now, to break bonds, we need energy, right? To break apart something that's bonded together, we have to put some energy in to make that happen. That's going to be kind of this big hill here on our activation energy, right? This part here is the bonds breaking. That's to break those bonds. We have to put that energy in. Now, when we form bonds, making new bonds releases energy. That is the down part of our hill there from our energy diagram. The bonds forming is going to release some energy. Whether our reaction is endo or exothermic is determined by whether the amount of energy released from forming the bonds is greater than the amount of energy required to break the bonds. If, in this case, we get more energy out of the bond formation, it's exothermic. If we get more energy out of, or if we need more energy to break the bonds than we get out of making them, it would be endothermic. So we can estimate that potential energy change by adding up all the bond energies for all the bonds we broke and in all of our reactants, and then adding up all the bond energies for all of the bonds we formed in the products and subtracting the two, right? We've talked a lot about enthalpy is products minus reactants. And so we take all of the bonds formed in the products minus all of what we had to break in the reactants. And if we end up getting a negative number there, then we're going to end up having an exothermic reaction. If we get a positive number there, we get an endothermic reaction. So here is our kind of equation for that to take a look at those. Bond energy is how much enthalpy is required to break or form the bonds of 1 mole of that gaseous molecule. They do all this study in gases because they're easier to study when we're looking at pressure, volume, all that good stuff. We know all of our gas laws. That's how they do all this stuff in the lab, is by looking at things as a gas. Our bond enthalpies are often listed as a positive value, which is what we use for bond breaking. When a bond is formed, we flip it and we make it negative, right? Because we have energy released when a bond is formed. So any energy that enters the system, remember, positive enthalpy, endothermic, positive enters the system. Energy leaving the system, that's negative enthalpy, it goes out, exothermic, right? So here in this equation we have the delta H of our reaction. If you've never seen this symbol before, this symbol right here is the capital Greek letter sigma, and in upper level math, that capital sigma there stands for the sum. So it's the sum of all of the delta H's of the bonds being broken, plus the sum, right, sigma sum, the sum of all of the delta H's of the bonds formed. Because all of the bonds formed have a negative enthalpy value, you're going to be taking all the bonds being broken minus all of the bonds being formed. If that comes out to a negative number, right, it's exothermic for the whole reaction. If it's a positive number, we get endothermic for the whole reaction. So let's take a look at a practice problem with this bond enthalpy. Now this big chart over here tells us a bunch of bond enthalpies, bond energies. Now on the AP exam, they're probably not going to give you a giant chart like this. They'll just give you the values that you would need for the problem that you're doing. But this is the kind of thing you would find in like a college level textbook. Or if you were doing some lab research, you would look up all these bond enthalpy values. These are all things that have been experimentally determined over time. Now, we're going to calculate the enthalpy change of this reaction. The CH4 plus O2 turns to CO2 and H2O. That's the combustion of that CH4 molecule. Now, we're going to identify all the bonds that need to be broken in the reactants and all the bonds formed in the product. So here in my reactants, my bonds that need to be broken, I look at my CH4 and what kind of bonds do I have there? I have carbon to hydrogen bonds, right? And how many of those bonds are there that I'm breaking apart? There are 4 of them, right? I have a carbon bonded to 4 different hydrogens, so I have to break all 4 of those carbon-hydrogen bonds. Where is that on my table of all my values over here? So I can keep track of that. I look over here for carbon bonded to hydrogen. I find that right here. Carbon-hydrogen is at 413 kilojoules per mole. Also on the reactant side over there, I have the O2. Right, so O2, it tells me my O2 bond down here. O oxygen has some different values for its bonds. Right, you can see here that there's an O to O single bond there, and then there's an O2 bond down here. So those have different values. When we're looking at O2, we're not going to look at the OO single bond. We're going to look at the O2 that's down here in that multiple bond section, that 498 kilojoules. How many O2 bonds are there? There are 2 of them. Now wait, Mr. Myersko, it's O2. There's only one of those bonds. There's 2 oxygens. Keep in mind that we have to take into account our stoichiometry, right? There's 2 O2s. I have to break apart the O2 bond for both of them, and so I have to have 2 of those O2 bonds being broken. So, now that I've done my bonds being broken, I'm going to look at my bonds formed and see how many of those I have and what kinds. Well, in CO2, we have carbon-oxygen bonds. Now, a big question. Are we doing carbon-oxygen single bonds, or are we doing carbon-oxygen double bonds? Well, you should see something in here that's going to give you a hint to that. But if you didn't have this table, we would have to look at the Lewis dot structure, right? The Lewis dot structure of our CO2 looks like this. Right, we have carbon double bonded to both of the oxygens, and so that would tell you we're not using the carbon-oxygen single bond, we're using the carbon-oxygen double bond, and specifically if you look down here, it has its own value for CO2, which we're going to be using that one because we're making CO2. So we're going to put down here, we're forming a carbon double bond to oxygen, and how many of those are there? There are 2 of those, right? In CO2, I've got 2 double bonded oxygens. Then for my water, my H2O, what do I have going on there? Well, I'm making some oxygen to hydrogen bonds. I'm making oxygen to hydrogen bonds. Looking at my table over there, they have to be single bonds because we're working with hydrogen, and oxygen-hydrogen bonds are right there, that 467. And how many of those are there? We have a total of 4. Each water molecule has 2. There are 2 water molecules for a total of 4. So we have a total of 6 bonds being broken on the reactant side, 6 bonds being formed on the product side. Now that we know what bonds are broken, what bonds are formed, and we've already done the next part, listing the number of each type of bond broken. We did that already. Now, let's calculate the total enthalpy of all of the broken bonds. So, for our delta H of the bonds broken, I have 4 of the CH bonds being broken, which is 413 kilojoules per mole. Plus 2 of the O2 bond there, which was the 498 kilojoules per mole. So my total delta H of my bonds being broken, I'm going to do that math, add those up, 4 times 413 plus 2 times 498. Gives me a total of 2,648, which I'm going to round to 3 sig figs and do 2,650 kilojoules per mole. Now we're going to do the same thing with the bonds formed. I don't have a ton of room to write down there at the bottom, so I'm going to try and see how much I can squeeze it in here. But we've got delta H of the bonds formed. Remember, these are all negative values because bonds formed release energy, have that negative enthalpy. So here we go. I've got 2 carbon-oxygen double bonds that come from the CO2, which is going to be 799 kilojoules per mole. Plus, I've got a total of 4 oxygen-hydrogen bonds, which have a total of 467 kilojoules per mole. And when I do that math and that addition, I've got 2 times 799 plus 4 times 467 gives me a total of, if I round to 3 sig figs like I did before, 3,470 kilojoules per mole. So there's my total enthalpy of my bonds broken and my bonds formed. Now, to find my overall reaction enthalpy, right, I just copied these over so that we have our numbers here. We just did the math on the other page, so I'll just copy them right now. Bonds formed was 3,470, and my bonds broken that we did was 2,650. Now, to get my overall enthalpy change of the entire reaction, delta H of my reaction is to take my, and I'm sorry, I should have put this before. This is, for the bonds formed, this is a negative, right? Because we have negative enthalpies for all of these. I made a point and then I didn't write it there, so that's my fault. I'm sorry. We're going to take those two numbers and we're going to add them, right? We're going to take our 2,650 plus negative 3,470. And that'll give me my overall enthalpy of reaction. So 2,650 minus 3,470 gives me a total of negative 820 kilojoules per mole. That is my enthalpy of this reaction. So to burn 1 mole of the CH4, it would produce 820 kilojoules of heat, exothermic, right? Because it's negative on that enthalpy of reaction based on those bond enthalpies. So this is going based on those bond enthalpy values. I got one here for you to try as well. You can always pause it. You can grab this one and work on it with that same table there. How much heat do we release by combusting propane, the C3H8, doing a combustion reaction there? That one you're going to have to balance the equation, because if you look, it is not balanced there. So you'll have to balance your equation and then do your math to find your overall enthalpy change of reaction. And then the second one there is that below reaction endo or exothermic. Calculate there. So 2 more problems for you to try and calculate your overall reaction enthalpy based on those bond enthalpies. You can try either of those. Make sure that they're both balanced before you do. And that's it for section 6.7. So thank you guys for watching, and I will talk to you guys again very soon.